Is that too loud? Are we good? Okay. Okay. So here's what does matter, is that the behavior, and I talked about this a little last time, and I want to say some more now, is that the behavior is robust. So in other words, you change the couplings a little, and by something physical. So this is where this distinction I made between the fermionic and the spin description of the Ising versus Kitaev chain is very important. So you change the couplings by something that could happen in your physical system, and then whether the behavior survives. And so one thing I mentioned, so in Ising case, it's certainly easy to imagine you could get a stray magnetic field. If the Ising chain was your physical realization, and I mentioned this term that was something like, I don't know, capital H, sigma Z at some, oh, that's right, this was the joke, we had to call it B to avoid something else, just at some random point Z, and so that breaks the Z2 symmetry. But in the fermionic language, so notice this operator anti-commutes with -1 to the f. In the bosonic language, -1 to the f flips all the spins, so that thing will anti-commute with that. In the fermionic language, -1 to the f just tells you the number of fermions mod 2. So -1 to the f anti-commutes with. So it's odd in fermion number, and you don't want to add, it's unphysical to add a single fermion to your Hamiltonian, because fermions are non-local objects, right? So this wouldn't be a local Hamiltonian. You can't add a single fermion or a trilinear in fermions to a Hamiltonian. So that won't ever happen. Actually, someone pointed out to me, there was a discussion of this angels on the head of a pin issue on stack exchange, and Xiaogan Wen sort of said it in a funny way, but that was his observation. He says that it's really he didn't call this a symmetry even, which I think is maybe not the right way to say it, but he didn't even call it a symmetry. He says fermion systems always have that, which is certainly correct. So that's sort of, he was taking the view that, again, don't worry about these things. So this is what matters. So that was one example of something property that you see what we're doing is robust. So first part of today, I'm going to be a little more formal and then say a few more things that indicate that behavior is robust. So one of the things this eightfold way and all that stuff tells you is about topological invariance. So I'll get to that in a few minutes, but I want to say one thing as long as we're still on about edge modes. And so, for example, this edge zero mode we talked about, two of them, one at each end, psi 1 and psi 2, those survive. It's really easy to see, so I'll show you that. Those survive even if we allow the couplings to be disordered. So sometimes people say that you let the couplings be random. That then leads to questions like Slava asked Frank, which was that, well, what measure are you using to integrate over random? So by disordered, I mean you just change the couplings around in some random to you fashion. And in this case, what I'll show is that for any time I change the couplings around, this zero mode survives as long as, well, one condition is obeyed. Okay, and so that's what we would say, just disordered. So I'm not thinking, so when you say randomness, that sometimes implies you integrate over some ensemble of all these things, but I'm not doing that. I'm just going to say I'm going to change the couplings around and all that. And so in particular, if we take our Ising couplings to just vary in space. So we would have this. And then you can rewrite this in terms of the fermions. So I haven't changed the form of the terms at all. I just changed the coefficients. And so this will still be then the fermion bilinear 2j minus 1, 2j. And this will be 2j plus 1. I think there's a minus sign there, but it doesn't really matter. Okay, and so this is sort of completely disordered. I can take the h over j's if you want. But now if you go back, so if you remember the way I computed this operator psi, remember we started out with the operator psi equals psi 1, and I says, well, that commuted with the Hamiltonian with h setting little h equals 0. Well, so this commutes with the Hamiltonian. All I have to do is set h1 equals 0. I don't have to set all the h's equals 0. I can just set h1. But now I turn h1 on. It doesn't commute. And then I got the term h over j psi 3. Remember, because they canceled the psi 2 bit. Well, so now if we look at this and with the couplings here, all that happens if I allow those to vary in space is it goes through exactly as before, but it'll be h1 over j1. But then I keep going. Remember, this then didn't commute with something, and I had to add another correction. So I'll just say it in words, but if you go back and look at your notes, it's almost obvious that the next one then just goes that. And you can tell because it's just term by term, and this iteration allows this to happen. So you can now guess how this is going. And so forth, up to the other end. So that's a really good sign that what you're doing isn't super special, that if I allow these things to vary a little, which can certainly happen in either the fermionic or the bosonic thing, if this were your real system, this thing still survives. So what I mean by survives is now even with this time-varying Hamiltonian, what I get is h, the new psi, with the variation is still just going to give me something exponentially small. Okay, and the one other thing we had to check, remember, was that the thing was normalizable. It would be sort of useless if you square it and it came back to infinity. And so remember last time we just squared it and we got these coefficients. And again, if I just put these things in their new form, all you get is this, and so forth. And so then the one other condition, I said I need one condition, as well this thing just needs to sum up to converge. So that's the same as last time. Okay, so that's a good sign that this behavior is robust. You'll get the edge modes even if the couplings vary. We preserve that C2 symmetry, but fermions do that automatically. So we're good. That's a good sign. Any questions about that? And I didn't say anything about time reversal or charge conjugation. I just constructed it. These are free fermions, so often you actually compute things. And here we go. We just computed it. Okay. All right, so this was for open boundary conditions. And one of the things I said briefly, but then people asked me about it, and I want to make clear. For a topological phase, which I haven't really defined what it is yet, I'm going to do that in the second half today. I figured this is more formal. I would do that in the first half. I'll do some little more qualitative things in the second half today. But let me say it important now. So topological order does not require edge modes. There are very interesting topological phases. So either edge zero modes in this case or gapless edge modes in higher dimensions. There are very interesting topological phases that do not have edge modes. But when they're there, they're a pretty strong sign. And when they're there and when they're robust like this, that's a pretty strong sign that there is topological order. And the edge modes form one of the most interesting pieces of physics coming out of phases with topological order. So much of the effort of both experimental and physical is to see these things, but I emphasize they're not required. There's perfectly good topological phases where they're not there. Okay? And so, yeah. That's right, even in the presence of the boundary. So you take, right, yeah, good. Thanks for clarification, absolutely. So even you take a topological system, you put it with a boundary, and you will not see gapless or edge zero modes. They're just physically not there. But it's a still, and maybe I can mumble a little bit. I did at the discussion yesterday about when that happens. We're not going to, I don't think I'll discuss any of those cases, but just to make sure that's clear. So, so the point is this is a useful probe. This is a way of seeing it, but obviously I just told you this isn't the only way. So maybe it would be nice to have another way to see whether there's topological, some form of interesting topological order. And so now for the first half this morning, I'll tell you about another thing. So this is what the classification, the BD1, D1 does tell you. It gives you this table that when you impose the symmetries, it tells you that there are these topological invariants. So, and I've mentioned this a few times, that what happens is you look at the Fermi surface, you notice qualitatively different behavior. So, or I should say qualitatively different properties of the Fermi surface. And I'll show you very explicitly, I should say just the Fermi surface, Fermi C, in different cases as something to do with topology. And the example I gave is a really nice example of that. So let me explain that. And what I'm about to tell you is in a bunch of places. Again, this review article I mentioned by Jason LSE is a very clean, nice place to see this. All right, so I wrote down oh, that's right, there was some homework. Hope you did it. Those of you getting graded, better show it to me, right? But I gave you this big Hamiltonian in terms of the C's, in terms of the size, and in terms of the spins, and I should check that all of them are the same, at least up to 2s. And so let's look at the most general one of those, Ising, but where there was this sigma y term in the spin language. And this was this one involving C's. So let me write out this in, okay, well, let's write it out anyway. Sorry, just to remind you, in case you already forgot, since it was 2 whole days ago. Yeah, there we go. So this was the Hamiltonian. So I think this is the same normalization I used then. So it's good to remind us, anyway, what's going on. Okay. So this was the most general Hamiltonian. If we showed, well, you showed in the homework, the T equals delta was Ising. All right. So remember these terms. This is just a chemical potential for the fermions. This is just the usual hopping term for the fermions. So we discussed that in the very first lecture. And this is the superconducting pairing that you get from potential, at least if you do it right, you put a superconductor up right next to the wire and do things right. And that's been the focus of a lot of effort by a lot of people who came up with nice ways to really induce that coupling. Okay, so then you go through the homework, but now I'm going to specialize. So I'm going to do one slight cheat. Well, not a cheat, but I am going to simplify the problem to get this topological invariant that I keep talking about. I'm going to assume translation invariance. I'm going to let the couplings vary a little bit, but let's assume translation invariance. So in other words, we're going to do periodic boundary conditions instead of open. Okay, so again, this is more now if we're in theory land because it's pretty hard. I guess sometimes they make rings of things, but it's harder to make a ring of these things. Okay, so that's things. So then you can Fourier transform. So you can do that construction I did with the matrix and commuting and all that. And like I said, what we did for just the plain Hagen, just finding the eigenvalues of that matrix are always sort of linear combinations with Fourier coefficients. And so then you Fourier transform. And we get the C of k equals something like e to the I k j C of j. Maybe there's a minus sign. I forget the conventions. Something like that. So now when you grunge through, so this would be the traditional way people would deal with this anyway. Like I say, it's totally equivalent to the way I showed you. And you get a bunch of things. So I'm going to skip that part. Oh, I guess we can make that a homework problem, but that's an easy homework problem. Okay, so homework. Again, check my 2's. But now I can write the Hamiltonian in the following form. So you sum over all the k's, and this is what Fourier transformation buys you. It makes it easy to solve this thing. That's why people do it. And I can even write it in a nice matrix form. CK dagger, C minus K. So the Hamiltonian looks like that. And the half kind of prevents some overcounting, and you can check the 2's. Well, so that's the homework. Check the 2's, check the minus signs, and all that. But up to phi to minus phi, minus signs, etc., that's certainly correct, and you'll check everything. Okay, and so notice this is C dagger of K, C of minus K. You think that has the same momentum. This would create a particle of momentum K that annihilates a particle of momentum minus K. So this thing is the same momentum and this versa. Okay? So let me just then write this thing in the form 1/2 summa K, and this is now capital C of dagger K H sub K CK, where this is just this vector, that's that, and that's that. Okay? So this is now how you can get, now you can, I'm not going to do it again, but remember I made you show what the energies were, and obviously it's just each K. So the point of Fourier transform, it splits all of the states. So in this hopping Hamiltonian, of course, all the different C's are coupled. And what Fourier transformation does in a translation invariant case is it kind of decouples all the different momentum modes. The only thing that end up coupled are K and minus K. So then all you have to do to get the eigenvalues, the epsilon sub K's, are just diagonalize that 2x2 matrix, which then is pretty obvious why it had the form that we talked about. Okay, any questions? Good, so that's that. So now let's look at this thing. And in fact, I said I was going to, I'm still going to assume translation invariance, but let's just look at that thing now. And in fact, I can then make a more general form. It's a slightly more general form. So H sub K is a 2x2 matrix. So in that, so now let me just let that be a more general 2x2 matrix of the form h sub k equals, I'll write it as h sub x, tau x, plus h sub y, tau y, plus h sub z, tau z. So these are just coefficients. And these are the Pauli matrices, and I call them taus instead of sigmas, so you didn't get confused. The taus are just acting on this internal space here. So, e.g., so here, for example, I guess h sub x, by here I mean there, h sub x equals minus t cosine k minus mu. What's the other one's h sub y? Equals, sorry, that's h sub z, sorry. H sub y equals, I guess, so delta sine k cosine phi. And h sub z equals h sub x equals, I guess, delta cosine k cosine phi up to twos and sines, not i's. Sorry? Sine k, sorry. Oh, sorry. I got these sine k, cosine phi. That's right. Yeah, sorry. Sine k, sine phi. Yeah, thank you. Yeah, that's very important, in fact. So one thing to notice, note these vanish. At k equals 0 and k equals pi. That's the important thing. And so those vanish. And in fact, that's now a more general result. Even for the more general Hamiltonian, even if we don't take this one in particular, any Hamiltonian of this form satisfying, well, where we got a matrix here and satisfying this satisfies that. So let me show that. Okay, so now, well, hold that thought. I'm going to show that more generally. Must apply here. And again, so the idea is we're trying to be as, try to be as general as possible. So now let's forget the detailed Hamiltonian. All we have is that with those and h sub x, h sub y, and h sub z, well, functions of k, I should emphasize that these are functions of k. X, y, z are not, well, they're in this tau space, labeling that. So, but they're all functions of k. The x, y, z are not real space. Okay, but then the thing you can note is that this capital C, so if I take the combination sigma x, C, this is capital C sub k, if I take it dagger, and then I transpose that, well, so what that equals to is C minus K dagger CK dagger transpose. That's just the definition of capital C. Then that's C minus K, C, K dagger transpose, which then if you just look is C minus K. So there's a little bit of redundancy in this. So if I take dagger transpose of that thing, I just get C of minus K. So then another homework, a nice simple exercise, is just by plugging that in there and massaging it around, what you find is that you get an equality in that h sub k, so you get, sorry, tau, and sorry, I wrote sigma, not tau. This is tau. So tau sub x, C, sorry, no C sub k. So tau sub x, H transpose H minus k, tau sub x equals minus HK. Okay, so again, so that's homework to check that. It's not hard, well, it's not hard, but it takes a few minutes of careful thought. So you plug it into that expression for 8, and you do dagger and transpose and stuff and follow things around. The minus sign comes because C's anti-commute. So, all right. So not hard to show, just a little bit of patience. A little bit of care, I should say, not patient. Care is the right word here. And so then what you get is this result that I just alluded to. You get in general, for this has to be true, then h sub x of k then has to equal h sub x of minus k. All right, and so even slightly, even more general result than the vanishing that I mentioned. Same for h y's. But h z's are not minus itself. Okay. So there's the results, and the explicit expressions I wrote out a few minutes ago certainly satisfy those. Remember, hz depended on cosine k, but hx and hy depended on sine k, so which obviously satisfies those things. Okay, any questions? So that's good. That's nice. And so then what that tells us in particular, of course, quite obviously it says that hx of 0, k equals 0, equals hy of k equals 0, has to be 0, proportional sine k, that works. But here's now another thing that if you're not used to condensed matter physics, you have to think about. K equals pi and k equals minus pi are the same thing. And, you know, if you're condensed matter, you've heard this a billion times, but you have to think about it for a second. Because the reason why, so we have this Brillouin zone. So yeah, for those of you who aren't used to these things. And the reason was why I was pedantic and wrote out what the Fourier transform is. Remember, I wrote the Fourier transform and an e to the ikj in it, you know, sum on cj. That was well, obviously, if I shift k by 2 pi, these are all integers, so they're the same thing, right? So you shift k to k plus 2 pi, and it's irrelevant. That's how you get the Brillouin zone. You say, well, you know, this is meaningless to shift k to 2 pi, so thus, what's the point in doing it? So thus, these modes are the same thing. So thus, as long as under assumptions that h sub x of k is continuous and all that sort of stuff, that says that, well, h sub x of k equals pi has to equal h sub x of k equals minus pi. Those things are continuous just because the shift by 2 pi. But of course, the relation we just derived over there says that's equal to minus h of x of k equals pi. So that has to be 0. I mean, indeed, we saw that. It said sine k, so sine of pi vanishes as well. And likewise for h sub y of pi. Right? So just that seemingly innocuous fact, it was just, well, sort of redundancy and parametrization, and then just follow through gives you this result, and that's actually all you need to derive this topological index. So, yeah, let's erase this. Yeah. Yeah. His comment was on k to pi, shift by pi. Yeah, his shift was shifting k by pi. So that is in principle different, although people then flip it over, which I think is okay. I mean, as long as you're careful what you mean, it's okay. But his point was that, well, you could design an experiment to see the difference between those two things, which I'm not sure you can here, actually, after I thought about it. But anyway, but certainly in general, that's a difference. No, not k. K to 2 pi, everybody agrees. That's just, I mean, it's a meaning. Look at that. I mean, it's utterly meaningless. Now, people do things like understanding if you continuously take k from minus pi to pi, what happens? we're going to do a variation on that. And this adiabatic continuation things can be very important. But anyway, so just settle. Yeah. No. Particle hole symmetry is typically taken as unitary. Charge conjugation. Particle is anti-unitary. No, because it's Hermitian. These are, these are her. There's some subtleties with how you define hermiticity. The way I define hermiticity, when you take, the hermiticity, the Hermitian conjugate of two fermionic operators A, B, is equal not to minus B dagger, A dagger. I take it to be equal to B dagger, A dagger, I think. Sometimes in particle physics they put that minus sign in because it's more convenient. And then you run into then you run into some confusion, so maybe then sometimes you have to take charge conjugation to be anti-unitary, I forget. Yeah, CP and T, back when I was in particle physics, CPT was, well, P's okay, but C and T I was always, with fermions, are always horrendously confusing with the sign. No, this is totally Hermitian. Just check. I wrote them both down, so that's the homework exercise. You can just check. The original one is quite obviously Hermitian with that definition of hermiticity I just gave. And then make sure that the expression with C's. But I think it's pretty obvious that these are all Hermitian, and I think it's okay. Yeah. Yeah. That's right. Did I leave an I? Is the complaint I left an I out somewhere? I don't know. So I should have had an I in front. I didn't write it in my notes. I don't know. It depends on the basis. And like I say, all these questions are simply, how you define your C's. I think I'm pretty sure it's okay as written, but okay, add that. That's right. You just made the people doing the homework have to now check carefully. All right, so add that to the homework exercise. Check that my convention, as well as checking my I and minus signs, check that everything is Hermitian with some appropriate definition of hermiticity of your things. And tell me what that definition is, because there might be some subtlety. Yeah, because if you get a minus, if you dagger that, you have to be a little careful. So, yeah, because I think C daggers are defined then with the minus sign. Anyway, it's definitely okay with the appropriate conventions. Okay, so right, so we've now shown this key result, which was true certainly for our specific example, but it's a more general statement. We're still assuming translation invariance, so it's not as general as the case I started out the hour with. But, okay, we've got this again, sort of innocuous fact, but then that says that at h equals, at k equals 0, well, the only term that can survive in this is the last one, so is just h sub z 0 tau z. But likewise, at k equals pi, so I should have written k equals 0 here. Okay, that's the only consequence. Again, obviously true for the Hamiltonian I wrote down at the beginning, the specific one. Okay, so that's whatever. So that's there. But now, let's consider, now this is the slightly subtle part. So let's consider now So you can think of, before I say consider, you just think of now as, this capital H is just some vector, right? Just consisting of cal x, cal y, cal hx, cal hy, and cal hz. All right, it's just some vector. Let's just normalize that vector. So then obviously it's the obvious hx squared plus hy squared plus hz squared. So I can consider now a normalized vector like that. As long as, of course, this thing is not 0. But now here's where this gapped versus gaplessness comes in. Because you think about, remember we had these dispersion relations that I made you work out, the ones that looked like that, right? So notice here, whether you're up here or down here, this thing never has any 0 eigenvalues. Right? So then you could normalize it like that. And in general, you think about it, because of this sort of h to minus h symmetry, and this is this charge conjugation symmetry if you wish, the only times you might get some point as we vary this around, like we showed in the Ising when you take h equals j, or in the hopping model when you took little s equals 0, then these closed. Okay? But the point is, those are the gapless points. Because when this closes, then again you have excitations that you can make that have arbitrarily small energy. So all those words say that this thing is always non-zero if the system is gapped. So this is where that piece of physics comes in. So again, you have to prove this rigorously, you have to make assumptions about continuity, blah, blah, blah. But this, I hope, is obvious if you don't worry about proving it in all generality. Is that clear? Please ask if that's not obvious. I just said. So that vector will always be non-zero. If you have a 0 eigenvalue, then it's gapless, assuming it's continuous. So it's not like, remember I drew the situation before, what I said for open boundary conditions, this where it looked like this, and I had this 1-0 mode there, the one I computed that I just discussed at the beginning. So that's different. So here we're assuming that H is continuous. So if I do have something that's 0, it has to be that, and it has to be gapless. Then there's H sub k's that are very near to it. And so let me say, I guess that's the condition. H sub k is at least piecewise continuous. Okay? So I can now talk about that vector. And so now that what we're saying is that h hat with this result at 0 is equal to some number, just call it s sub 0, sorry, is just some number s sub 0, which is equal to plus or minus 1, right? Because I'll just normalize that vector to be 1. So I'm just normalizing this vector h to be thing, and then h of pi is again, for the same reason, plus or minus 1, because it's only, so h sub z is 0. Right. And then, well, obviously h hat sub x and h hat sub y of 0 are 0. Is that clear? Why that is? All right, so now people who know about indices, when something is plus or minus 1, you think about it. But so now again, under the assumption of continuity, so now if we assume it's, again, h sub k is continuous, well, what that says is, so now h sub k takes values on a 2-sphere, h hat sub k, right? It's a unit norm 3 vector, so that means Look at that. And I've said now, because of this condition, that at s equals 0, it has to be plus or minus 1. So let's say s0 equals 1. All right, well, now I change, I continuously sweep from k equals pi, just change it. And again, I'm assuming it's a continuous function. Well, so what happens is this will move around. It can be any value. It doesn't have to be 1 anymore because hx and hy are 0. But then when I get all the way to pi, it has to come back to either 1 or minus 1. So one possibility is, well, it eventually ends up there, and this would be then s pi equals 1 as we sweep out. But another possibility, of course, is that we move around and we end up there. So this would be, say, s0 equals 1, but s pi equals minus 1. And so this is now finally, long last, where topology comes into this. Because I can now change my Hamiltonian around as much as I want, but unless I close the gap, I can't relate the two cases. The point is, so if I continuously deform the Hamiltonian, the full Hamiltonian, then the product s0 times s pi cannot change. If you were to write s0 s pi, well, so you could change conventions and flip both of them, but you can't flip just one of them by changing conventions. So this is our Z2 topological invariant. And really the most simple, beautiful example of this. So that's why we kept saying it's a property of the Fermi C. You just got some function h. And so obviously so that means I take that Hamiltonian I wrote down, I change around hk every I want, so it doesn't have to be sine k. I could add sine cubed k, or whatever, however I choose to add my Hamiltonians. You add next nearest neighbor hopping, you add all this sort of stuff, as long as, like I say, you preserve translation invariance, but can add lots of different kinds of terms. Not going to change this. Unless, so here's the big unless, capitalize that. You close the gap. Because then the vector, I made the point of saying then the vector h hat doesn't make sense. But that's a phase transition. When you go to something gapless, that would be a phase transition. If you look at the explicit things I wrote down, so at Ising, you would find h equals plus or minus j would be the point at which it's gapless, which we checked, of course. But this is in the fermionic language. So we've seen now that, well, the Ising transition, this is the Ising transition in fermionic language. You tune the parameters so that you swap one phase for the other. So this now explains, finally at long last, what the transition is at Ising in fermionic language. This is why no one thought about this till Kitaev, and that's why people call the Ising model in terms of fermions the Kitaev chain now. Questions? Yeah. I'm sorry, can you say it again? Okay, sure. Okay, so we showed because of this symmetry, let's just take the example of sine k. So they vanish at those places. Now I continuously deform. So now I just sweep through k. So in the example I gave, it's an actual function, right? You ask what happens to the function as I change k from 0 to pi. So as long as the cal h is continuous, well, it'll just move around. It no longer has to point in that direction because cal hx and cal hy are now non-zero, right? So I'm looking at the vector. So remember I had the vector cal h equals cal hx, cal hy, cal hz. But then I'm going to look at the unit version of that. And so then again, hx. Okay, so that's just scaled, and as long as it's gapless, I can always do that. All right, so now, but we know at k equals 0 and pi, this is 0. That's 0, but that's then plus or minus, because this is unit norm vector, so it has to be plus or minus 1. So now it's just a simple topological fact, right? So I start with k at k equals 0. I follow this vector around. So the vector points at some place on the unit sphere. It's a unit norm vector. I just follow it around, and I just, depending on whatever interactions I've put in, it goes from here. Okay? And then you just ask, where does it end up? And there's sort of just two possibilities. Either it ends up there, like we had a sine k. It'll go from plus to minus, or minus to plus. Now I'm just varying k, but I'm saying no matter how, good. Right, these paths are varying k, so I just, this would be whatever k equals pi over 2. But I'm saying the path will change. Now I vary that, okay, so for a particular Hamiltonian, I get some path. Right. But okay, so now for a particular Hamiltonian, I follow the path. It will have to follow one of these two things. Now I vary the Hamiltonian, the parameters in the Hamiltonian, but preserving that form I wrote down. That's important. Preserving the form I wrote down. Well, now the paths will change, right? But the important point is the invariance is that no matter how I vary the parameters in the Hamiltonian, this path will not change. And that's the invariant. Good. All right, I'm glad you asked. That's important. You could. But you could. But there's nothing, but in this particular case, you could always deform that path. You go around, you go around the world, 15 times, and then at the North Pole, I can continuously deform that to not going around the world. Yeah, but that's okay. That's okay, because remember, all we're doing is varying k. And it's certainly possible. I mean, I can come back after pi over 2 if I want. I mean, there's no rule against that. Yeah. Yeah. Yeah, but we needed the sphere to see this point that at k equals 0 and pi, we're always this one point. Okay. But that's right. That's right. It didn't have to be a sphere. But on the other hand, I mean, topologically, a sphere is probably okay. But the key thing is we had to choose. Like I say, these were plus or minus one. You know, if it were, I mean, depends on the situation, obviously. But I mean, if you wish, that's the statement. The fact that it's a sphere, topologically a sphere, is the statement of gappedness. Because otherwise it wouldn't be. If that thing could be zero, then I couldn't do this. So that's if you wish, where this comes in. And so, yeah, of course, one can imagine, and one can, we'll take a break in a minute, but then I'll give you another example, just qualitatively, where the same kind of thing happens. Yeah. That's right. Right. Well, yeah. I mean, I could take translation invariant disorder and things like that. So, I mean, I could, and that would still work. And after the break, I was going to do it now, but since we could use a break, after the break, I'll explain there's a more general topological invariant that will even let you deal. Right, so this doesn't say one way or the other what happens, but I'm telling you the answer is that it's all still okay. As I indicated with the edge zero mode too, is a pretty strong indication that everything is going to still work with disorder, as long as you don't close the gap. Yeah. Yeah, so if you close the gap, just like with that edge zero mode, so closing the gap, I should have emphasized this. Remember, normalizing that vector becomes unnormalizable precisely at h equals j in the other case. So that breaks down. So everything all breaks down. So anytime there's a transition, and obviously if I take a more general model, it won't always be at h equals j. If I add different couplings, the thing will move around. But as long as I don't close the gap, that's really, really important. So the answer is I can add disorder, but not enough, as long as it's weak enough disorder to not close the gap. That's the important thing. Good. Yeah. Well, this is my, if you wish, this is my definition of topological order. Yeah. Yes. I mean, we're in 1D, right? So the notions of what topological order is, so there's no one uniform definition, at least that I know of topological order, that sort of works for everything. It's the usual, when you see it, and so you can give sort of lots of parallel definitions that are certainly equivalent in every case we understand, maybe. Well, that's what we're going to talk about next hour. Okay, yeah. Right. Yeah. Yeah, you mean putting an arrow on that in either that way or that way? Oh. Yeah. Oh, closed in the down. Yeah. No, so, right. Oh, and that would be the same for this one, going from bottom to up to down. Yeah. Right. I think that's a gauge choice. In other words, I can redefine my 90% sure the answer to that is you can redefine your it's the same Hamiltonian, but just do a unitary transformation on your Hilbert space that would change, would flip the sign, but it would flip the sign of both of them. So that's not an invariant notion. That's just it's like a gauge symmetry. It's not even a gauge symmetry. It's just a parametrization symmetry. But whatever unitary transformation you would do to the Hilbert space, you'll leave S0 S pi invariant. That won't change. 90% sure that's the correct answer. Yeah. Oh yeah, yeah. It's just this there. Yeah. Yeah, something like that. Yeah, so there's some. I think that's the correct answer too. That's right. Yeah. Right. That's right. And what I'm saying is in Ising, for example, H less than J and H greater than J correspond to those two cases. Yep. Good. And I'll give you a broader definition, but this I think is really very, and this one is very analogous to the more general case. Sorry? This is still free fermions, right? Yeah. I think I haven't discussed. I will either today or next time. I'll say some things. Either the. No, that's right. Yeah, but I think right. But this. Well, this wouldn't be in the first model because the first model, remember, didn't have the superconducting pairing. So the first model was just hopping fermions, so we didn't have the C dagger term. So in this language, like. They're free fermions, that's right. Yeah. Right. So this came, I mean, this whole structure, this whole thing I just derived only will work for free fermions. I will make comments, though, what happens when you add fermion interactions, though. This is it. Right. Yes, that's right. Yeah. It's the model I wrote down a little while ago. The first lecture was just hopping fermions, so that's a special case of this. If you remember, that would be delta equals 0 in the Hamiltonian that I wrote down, I don't know, a half hour ago. Oh, right. So what the hopping fermion model I wrote down is a special case of this, delta equals 0, special case of this, and you would find that the hopping fermion model would correspond to the topologically trivial one. It would correspond to one of these paths, the first model, the very first model I wrote down. Yeah, and it's critical too. That's right, it's critical. Thank you. Yeah, the very first one, the staggered one, then is non-critical, but yeah. So I'm just saying, so everything I've done to date has been a special case of the Hamiltonian I wrote down, I don't know, a half hour ago or so. You can, by setting delta and t. So Ising is delta equals t, hopping fermions. I guess the staggered fermions is not a special case of what I wrote down there. No, because the most general form of this Hamiltonian has C dagger terms, and you can't Well, okay, you can write new fermions. Yeah. Fine. Yeah. Okay. Fine. It's a non-local map of the original Hamiltonian. That's right. Yeah. That's fine. That's right. But then, yeah, right. But then you have these subtleties with plus and minus signs. So it's better to do it the way I wrote it now. Because, you have to diagonalize a 2 by 2 matrix to do this, and your eigenvalues are plus and minuses, so then you'd have to take two cases corresponding to plus and minus, which is precisely what's going on here, was what gaps it. So it would have a different dispersion relation. So the point is, you can map it onto that form, but it will have a different dispersion relation than. Yeah, you could define that. Yeah, and it was but then Frank pointed out the very first model is gapless, so you couldn't even define this. The very first model is gapless. The k equals pi. H is 0. So we better stop. We really need a break. So let's stop and we can do it. Okay, one more thing I should emphasize. I kept saying cal H is continuous. Of course, for that to happen, we have to take the system size to infinity, right? The levels are discrete, but when we take the L to be really large, then H gets to be continuous. And that's why this statement that H vanishing is equivalent to gaplessness, because it's continuous, and then there'll be lots of levels with energy near to zero, and those are the gapless modes. Typically 1 over L, but not, it could be 1 over L squared. There's lots of things possible. Okay, so let me, all right, so let me make a few comments. So just qualitative to ease our way back in to things. So one of the, the reason I went through this, even though I'm going to give you another topological invariant too, is because it's an example of a more general phenomena, and that's where the K theory and all this stuff comes in. In these, so what the classification lets you do is it tells you that for a given system with these given symmetries, there exists a topological invariant like the one I just described. And to give another example that's very closely related to the thing. So I'm not going to even define the system, but I'm just going to say a P plus IP superconductor. I'll say in words what it is, but not define it precisely in 2D, and that's 2 spatial dimensions. And so P plus IP, what that means, it's shorthand for P IPY. And what that tells you is what the angular momentum is of the Cooper, the orbital angular momentum is of the Cooper pairs in it. So there's a condensed matter, people have a very old way of understanding things in an effective theory called Bogolubov-Dijen, and in that, and so again, it's a free fermion system in a Bogolubov-Dijen approach. It becomes free fermions, and again, so then here it's almost the same as the situation we just did. In fact, the Kitaev chain is often called a 1D P plus IP superconductor because the topological invariant is essentially the same thing. And so here, though the Fermi C, the Brillouin zone, is 2-dimensional. We have a vector K, and then again, so we have now this vector H of K in the same way. So again, it's written in terms of H sub K tau x plus, so exactly the same as before. So you don't even have to write it out if you don't want, but I'll be pedantic and write it out. H sub z tau z. So the only difference between what I wrote before and now is now K is a vector because it's 2-dimensional. And then if you consider a system where H of K, the magnitude of H of K goes, sorry, not the magnitude, where H sub K itself goes to some constant vector as K goes to infinity. So it doesn't depend, it goes to some constant pointing in one direction as K goes to infinity. Then the map we had this map from just the line, from the circle, if you wish, from K equals 0 to 2 pi, sorry, minus pi to pi, but then we looked at the 0 to pi section. But here what happens is you now then, when you have this, you have a map from the sphere, the 2-sphere, S2. Okay, so this is K-space. If this goes to a constant, so the point at infinity is all one point, and so it's a map from there to our 2-sphere if H is not equal to 0. So again, if it's never gapless, instead of having a map from the line segment to S2, we have a map from the full sphere to S2. So many of you have probably seen in various contexts, particle physicists do instant-time number. But no, there's an invariant, and topologically it's easy to see. It's the topo invariant is the number of times this sphere, the K sphere, wraps around let me just write this down. Yeah. That's because I made this condition there. I mean, so that's a particularity of the model. So if you have a situation where its K gets large, so you assume the Brillouin zone's very big and then look at that. Yeah, and then it goes to a constant. I mean, you might have a map from the, again, that would have still a topological invariant too. I think it's just not as easy to write down as the one I'm about to write down, but yeah. I think that has a top. Someone knows better than I do. I think that has a top. And so it's the number of times. So just think of a sphere. I've got to map a sphere, a two-sphere, onto another two-sphere. Well, I can wrap it around no times, which means topologically it's trivial. All the points on the first sphere go to, say, one point on the next sphere. Or I can have it just be the identity map, one sphere to another, and then that wraps around once. And you can think about it, I can wrap it around a negative amount of times. It's sort of as you go around the sphere in one direction on the original sphere, then it goes around in the other, like an anti-vortex. And so if that, but anyway, there's a number called the Chern number that describes this. I'll just write it down because it's cool. Yeah. Right, but I said this. Right. Yeah. Right. So you could do this with the torus either, but then that's a little subtler. So I'm trying to be simple here so this was just to give you an example that what I was showing you before was not some isolated piece of weirdness. And it looks like that. And did I get the 4 pi? All right. And so for P plus IP, then you get, I guess, C equals -1 for P plus IP. You do P minus IP in the standard conventions, you get C equals 1. And you can look in Jason Alcia's paper to see a little more detail on that. So anyway, and in all these other classes, so if you've seen people give talks on the 8-fold way or the 10-fold way, whatever they call it, all the time what this table has that they show you tells you what sort of topological invariant there is for these particular symmetries. But of course, then there's that table is only the beginning of the story, not the end, and there are lots of refinements. So one example that Frank's going to talk about is SPT phases. So that's where you have to assume a different, that stands for symmetry protected topological phases. So you have to assume an additional symmetry in order to get a topological invariant. So in other words, if you break a particular symmetry, you don't get a topological invariant. So an example in what we discussed was the icing. If we were doing icing, and then you have to preserve that Z2 symmetry, and if you don't, it goes away. All right, so that was comment number 1. So that's another example that's very closely related. Comment number 2 is that, we discussed a little, is that, in fact, I assumed to get the topological invariant I wrote down, I translation invariant, so I could write things in K-space. So that doesn't include things like staggering the couplings. You just have to shift what your K-space is. But in any case, that all will work there. But if you just want to take disordered couplings, like I showed at the beginning, what I described doesn't work, but the situation does. And the answer is kind of neat. So Kataev pointed this out in his original paper. So if you write the Hamiltonian, the Majoranas, so psi I, psi j. And then so that the Hamiltonian is some Hij psi I, psi j. I can put an I here if I want. I guess do that. So then H sub ij is a real antisymmetric matrix. So we wrote down that one with the H's and the J's. It's antisymmetric because I take the Hermitian conjugate, these change places, and I have to move them back and pick up a minus sign. Okay. And so what Kitaev says, I'll tell you the answer and then explain what the topological invariant is the sign of the Pfaffian of this matrix H sub ij. So sign, just plus or minus, so you get either 1 or minus 1. We know what the Pfaffian of that matrix is the following. So Pfaffians come up in physics all the time. For example, if you evaluate the Grassmann partition function, you get a Pfaffian. So as a result, when you solve the Ising model via Dimer methods, so this is what McCoy and Wu's book. So I talked about one way of solving the Ising model. Another very useful way is to write things in terms of Pfaffians and all that. But anyway, that's another story. I can talk about it a little more later if people want to hear it. But anyway, so with the Pfaffian of an antisymmetric matrix, well, first let me say the Pfaffian squared, it's the determinant. Well, what the definition of the Pfaffian is, I guess in physicist language, it would be I. Let's not use I because I'm using square root of 1, J2, J3 times H J1, J2, H J2, J3, H J3, J4, etc., and then some overall permutations of the J's. So let's just give an example, make it more obvious. So let's just do the system we talked about with periodic boundary conditions on. I guess this would be 2 sites. So the matrix will look like this: H minus H, J minus J, H minus J, sorry, H minus H, and then it'll be minus J up there and minus J up there. So in general, if a 4x4 matrix, Hij, well, the Pfaffian of Hij would be, so H12, H34, minus H13, H24, plus H14, H23. So that's that sum there. And some, there's some number there, I'm sorry. But we only care about the sign. Let's see if Pfaffian is proportional to that. Just number to count for the overcounting. So anyway, well, we can do that. That's H times H, so that's H squared. That one's 0, because H13 is 0. And H14 is minus J times J, so that's equal to minus J squared. So you get the miracle of miracles. The sign of this changes when H equals J. And that's not a coincidence. Again, that matrix, this was exactly the matrix that came up when we were when I was diagonalizing things at the beginning. So when this is 0, there's a 0 eigenvalue, and if it's continuous, if H or K is continuous, then we're all good, so it's gapless system. So again, this is, so sign of Pfaffian here is equal to then minus 1 for H less than J, plus 1 for H greater than J. And then this signifies the topological phase. And again, as you don't close the gap, the Pfaffian will of course change, but it won't change sign, because you would have to close the gap. So if this is 0, one way of saying this is 0, then it's gapless. So that's another way of saying it. That's a little bit formal, and I don't have a lot of intuition into that other than that it's correct and gives the right answer. So I think that's why I did the other way first, but I should mention that. And this then I can take, as long as it is a bilinear in these two, I don't need to assume time reversal invariance or anything. This is just the Z2 invariant. Maybe Frank will talk about what happens if there's... Actually, I will when I talk about interactions. Maybe I'll say a little bit more. But anyway. Questions? Okay, good. So now I think I'm going to be pretty qualitative for the rest of the lecture because I've done a lot of things today. So now I think someone asked correctly, to rephrase their question in a much less polite fashion, who cares? Why are we saying all this? You know, a lot of this stuff was known a long time ago. The first example of topological, this sort of thing was done in the context of the quantum Hall effect by Thales. Who's the K in TKNN? I'm already blanking. TKNN, who's the K? This is embarrassing. And this is on tape that I can't remember. Komodo. Yeah, sorry, Komodo. Thales Komodo denies a nightingale, right, to TKNN. So they pointed out this thing in the quantum Hall effect, and that was sort of tip-off. Well, this is sort of interesting because people were trying to answer the question I said Kitaev answered for the Ising chain. Well, what's an order parameter for the quantum Hall effect? Because there are transitions in the quantum Hall effect, but then how do you characterize the different phases? And between different plateaus, there's no local order parameter that you can write down. And then they pointed out there's this property of the Fermi surface, and the Chern number there is proportional to the conductance. So that was all marvelous. And like many things in physics, you go, well, that's really cool. Like with QED, you know, they say that's really cool, but you know, this is just some weird isolated example and something else. Field theories are just sort of a quirk. And so that's why, for example, field theories got, well, not forgotten completely, but people in the 60s didn't do field theories. They thought it worked for one example and it was cute. And so what happened, TCAN wrote their paper. They had a topological invariant. Whoopee, it was really neat. But then, and people even showed, well, there's other examples of topological invariants, but none of the models people constructed, I guess, were decided at the time the group decided that was not so exciting, so that kind of got forgotten and people moved on. It wasn't until 2000s where Kane and Millay wrote a paper saying, wait a second, I can construct other really simple models that have different topological invariants, and this is really interesting. And here's the reason why it's really interesting, because it should have been obvious from the quantum Hall effect. So again, it's an interesting sociological thing. Why did people sort of think about it for a bit and then, well, move on to stuff? And the reason it's interesting is because one of the common characteristics of topological order, so when one of these topological things is non-trivial, like we saw in the Kitaev-Ising case, often implies neat things like fractional statistics, fractional charge. So again, this is not a guarantee of these things, but it often does. Things like spin charge separation. One of the fascinating things about even the integer quantum Hall effect, which doesn't have really any of those things, but it does, for example, have this mind-blowingly precise experimentally accurate measurement of E squared over H. It's the most accurate experimental way of measuring the fundamental constant, well, the combination's E squared over H in the quantum Hall effect, and it's because of topology. So these systems have these nice characteristics, and this one is dramatic, and well, maybe I'll mumble about topological quantum computation a little later, but there's then lots of applications. So let me just say so the point is, again, these kinds of things happen in these sorts of systems. So that's not saying every system with this sort of behavior has all these things, but when you have these things, you think typically or probably always have that. And so that's the reason why all of a sudden people said, wait, there's all these systems and all of them have all these kind of interesting behaviors. And moreover, I think one of the sociological things that happened in between the early 80s when TK and N did their work and then the mid 2000s when Kane and Millay kind of greatly revived the subject was that people started to think about the applications of these things. So first, let me tell you, well, fractional charge, that's easy to say in a sentence. What that is, it's when the charges of the quasi-particles of the system, so the excitations of the system, is a fraction of that of the original. And the fractional quantum Hall effect is the most beautiful, a very beautiful example of that. So if you have a system in the one-third plateau, you look at the excitations, and even though the system is entirely made of electrons, you can experimentally observe effective quasi-particle charge of 1/3 of an electrons. Now, of course, since it's made of electrons, you will always have to have at 3 or 6 or 9 of these things. The universe does not have a fractional charge. But just like with our edge modes, you'll see that there's these localized excitations where in that region is only a fractional bit of charge. And if you think about a many-body system, there's absolutely no reason why that can't happen. So that would be another set of lectures I could give on how that's a perfectly sensible thing to happen. Even though your system is comprised of electrons, it is a perfectly sensible thing to have in some region, localized region, effectively only a fraction of that charge. So that's some neat many-body physics that we're not really going to talk about, but that's at least understand spin charge separation. Ask me later if you want to know what that means. But let me talk about fractional statistics very qualitatively, and then, well, I'm probably going to run out of time today, but then beginning of next time we'll talk about how that's realized in the Kitaev chain. So maybe I might get to it today. All right, so let me first say what that is. Many of you know, but it's always good to remember. So for the moment, let's confine ourselves to 2 spatial dimensions. And statistics, I hope you all know what that means. So that says what the wave function does under the interchange of 2 identical particles. So of course, if they're bosons, when you interchange the 2, so this is for 2 identical particles. So if I interchange the 2, well, I get a minus sign if they're fermions, a plus sign if they're bosons. Okay? So that's everybody, and this is true, it's true in 2D, but that statement is true in any dimension. And so in either case, well, we have psi squared x1, x2 equals psi squared x2, x1. Okay, so now again, topology starts to come in just right here when we talk about that. So in three dimensions, that's really all you can have. There's some subtle things that can go on there, but don't want to get into that. But in 2 dimensions, now you have to think about topology. So what do we really mean when we do interchange this 2? Well, this is some function, and we want to do everything continuously. And so what we mean when we do this interchange is we have 2 particles there. Okay, so x1 and x2. And what we mean by that is, well, we take x2 around, move it there, if you wish. So then our next state would be x2, x1. And then, of course, we can just shift it back to the original so that it looks like that. Or, of course, I could have gone around the other way. So now in 3 dimensions, these 2 actions can be continuously deformed to each other, right? I can do that, and I can just lift it out of the plane. So in 3D, the 2 paths continuously. So when I say deformed, I always mean continuously. Just lift it out and go there. So that's then the reason for this condition in 3 dimensions, is because there would be no invariant notion of anything that didn't have this, because this path, right, would be first do this and then do it back again. Could be. So interchange the two and then interchange two again, say if I'm using that definition of changing the two. But on the other hand, again, I can lift these out of the plane and I can continuously deform this into, well, nothing, right, just by lifting it out of the plane. So therefore, this is nothing, so this is why I have to get those equal to 1 in 3D. But in 2D, I don't need that to impose that condition. So, in fact, because the point is I can take this around, and I can take that around there, but my rule now to do statistics is I can't bring the particles together. This is why there's no real statistics in one dimension. There's no notion of a real physical boson or fermion in one dimension. You can talk about bosonic and fermionic operators, but there's no way to exchange two things in one dimension without having them cross paths. And if they're particles, well, they'll interact. And so then you can't separate the statistics from the interaction. But in 3D, and in 3D, well, you can separate them, but you can only do this. But in 2D, this path, and then that, so if you go take this guy all the way around, well, that cannot be continuously deformed. So I've got my one particle. That cannot be continuously deformed to that without interactions. So of course you're allowed to do that, but the point is when you bring this path through here, well, the particles get close together, and who knows what the wave function will do when you bring the particles close together. So it's, it's fine, but it's a statement about interactions, and we're trying to just ask about statistics. So it is entirely mathematically consistent in 2D to make, so this phase x1, x2. Okay. So again, most of you have heard this, but I think it's good to set it out. It's late. We talked a lot today. So. Right, yeah. No, yeah, so there's much about this, how would you physically do this? And so you think of, like adding like an STM tip, I'll sound like an expert, and then you would drag, you put them together and sort of have some attractive interaction there. So you don't bring the thing so close that it will tunnel, but then there's some interaction, and then you very slowly move it around, so you don't change, you adiabatically, adiabatic's the key word, adiabatically connect this state to that one. So as long as there's a gap, for example, and you put in very little energy and you do it really, really slow, you can do this. So it's just asking what happens. So I'm just saying it is mathematically consistent in a quantum system to have behavior such that now when I take two identical particles, or even two non-identical particles for that matter, when I take one around each other, so I just draw that again, and then I can have psi x2, x1 equal some phase psi x1, x2. Because I do it twice. So in the other case, this would violate adiabaticity. I do it twice, but I could deform that to the identity, and so I can pick up or pi or 0. But here, there's no consistency condition that prohibits that. Saying, well, of course, we're going to get to examples where we can do that, but That's right. well, there's a spin statistics theorem, for example, that assumes certain things, but not much. So, for example, yeah. Okay. So, but and here, yeah, and so you can talk about, so I talked about fractional charge, so there's various results that relate charge to statistics in 2D as well, but I don't think there's a well, I don't know. Good, any other questions? All right, so again, that's a story. There's been so much ado about it. I hope that all of you have at least heard this at one point, so this is just functioning as a review. But maybe what's now, okay, so these things, so particles that satisfy this are called anyons, Wilczek's name for any statistics, so it's a good joke, anions in chemistry. So they were called anyons, particles that satisfy this. And it turns out they exist in the fractional quantum Hall effect. Now, I say exist. They've never really, so what's been observed in experiment is fractional charge. Fractional statistics has been claimed to be observed, but the experiments are really subtle because trying to observe a phase, well, is really hard because in quantum mechanics, you might expect there's a gazillion ways you can pick up a phase. Again, my stray magnetic fields, all this kind of stuff. So observing this, and fractional quantum Hall experiments are difficult from the get-go. So it's a really feat. There have been claims, and there's no particular reason to doubt them, but it's really difficult, and it's only been a few experiments that actually observe this. Fractional charge is actually much easier to observe. You do shot noise measurements and things like that. Okay, so but anyway, but the fact that the anyons are predicted by various theoretical things, and these theoretical wave functions, so forth, have been tested in many, many ways, means I think nobody in their right mind would dispute that they exist in the fractional quantum Hall effect. Okay, so now, okay, so that's pretty cool. But then what people realize, well, once you go here, you can go further. And so now start to think of a system with degenerate ground states. Okay. And more, yeah, so degenerate ground states not trivially arising from some symmetry. So I don't mean things like you get by spontaneous, from some spontaneous symmetry breaking. So for example, the fact that we have degenerate ground states in icing is not obvious. The fact that these two things are exactly the same in energy up to this exponential splitting. They could have algebraically split. So let's suppose. So then what a non-abelian anyon is when you braid, so this, let's not use the word, when you do this exchange, so the system actually changes state. And this can happen when you have degenerate ground states. Because you move around, degenerate ground states, it takes in principle no energy. And what happened in this situation is something even weirder. So this phase is already pretty weird. But it can occur, and that was observed in the 70s, but it wasn't until after the fractional quantum Hall effect that people realized there are honest-to-God physical systems where this can happen, or does happen. But now this is even stranger. Again, mathematically possible. So the point is now, if we look at the ground state wave functions here, well, so now I put some indices on here, right? And when I exchange, and I'm going to give a very explicit example, I can then have some matrix that rotates you around in this among these degenerate ground states. So not just a phase. So the phase would be an example of a diagonal matrix with phases along the diagonal, and bosons and fermions, which have plus and minuses along the diagonal, but we can have an entire matrix here. The matrix has to satisfy certain conditions. But so psi is labeling the different ground states. So, if, for example, in Kitaev chain, we have these two ground states that that are protected, the topologically protected degeneracy between the two. Yeah. Right. So I'm just talking about at the moment. I'm running out of time. So when I start next time, I'll explain in the sense here. For the moment, just think of these as particles. But of course, only time these things occur is in some body system where these are the effective excitations. So just like I explained for fractional charge, you have some many-body system, and then you put in some energy locally, you'll excite some things, and then these are the things going around. But so different ground state in the presence of some particle. Right. So by ground state, I don't mean the ground state with no particles. I say you look at say 5 particle, let's just say 2 particles here. You have 2 particles here. Okay, so what I mean by ground state in the presence of the particles. Yeah, good, thank you. That's an important clarification. So whatever. So let me just say better to say, instead of that, let me just say the different degenerate states. Much better way of saying it. The different degenerate states. Yeah. Well, you can. Of course, you can see the degeneracies in the spectrum. No. Okay, no, absolutely not. Degenerate states. Let me just say, degenerate states are necessary, but not sufficient. But what I'll show in the Kitaev chain is, in fact, this happened. I need to explain how the Kitaev chain is 2 dimensions, but I'll. It depends on these non-local changes. I mean, a local change, it doesn't matter. That's a basis-independent local. So it matters spins versus fermions. Okay, that's an important thing, because that's a non-local change of basis. So within, this is independent of any local change of basis. Good. Any other questions? Because, I'm almost done, but, it's time anyway. But, yeah. They could well be the ground. That's why, I wasn't thinking. I mean, that was why it's a good question, because I wasn't. In the example we're going to do, it is the ground states in the Kitaev chain. But in this general picture that I'm giving, it's not the ground, because there we have these to hint ahead, we have those zero energy modes. But it generically does not have to be the ground states. But it's this. You're in some sector, and if you've got a gap system, once you go there, just moving it around slowly will leave you in that same sector. So well, that's what's going to happen. Yeah, so that's the next thing, which obviously I'm not going to get to this time, but I'll explain starting next time how this gives exactly that. Good. So anyway, this goes to at least start answering the question, well, why do we care about topological order? Because again, not in every system with topological order you see this thing, in many, many you do. And that's all of a sudden what everybody realized in the 2000s, and that wasn't just limited, one of these things, it wasn't just limited to fractional quantum Hall effect. There were a bunch of systems that, at least in principle, showed this behavior, and so that's why there's been this huge amount of experimental effort to understand this. Okay, good. Let's, I should say any more questions, and then we'll break for Frank. Okay, good. See you tomorrow.